Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry, Paper 3. In the Unit 1, we are studying about stereoisomerism, Part 1. In the Lecture 3, we will be studying about Fischer D and L notations, reactions of chiral molecules. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The various topics that we will be studying in this particular session include Fischer projection, D and L notation, assigning D and L notation to various compounds, mainly carbohydrates and amino acids, the interconversion of Fischer projections, and we will also be studying about reactions involving stereoisomers, basically generation of a chiral center, reactions involving centers other than the chiral center, reactions involving chiral center, and reactions of chiral compounds at the chiral center. Welcome to the next session. In this session, we will be studying about Fischer DL notation in the beginning. So the Fischer projection was first devised by Hermann Emil Fischer in 1891. He was the winner of Nobel Prize in 1902. He had worked extensively on carbohydrate, structural elucidation of glucose and many monosaccharides. He had extensively worked. So what he does is basically in this particular case, he wanted to represent the molecules in stereogenic way. That means each stereoisomer of the monosaccharide, he wanted to give some notation. So this is basically nothing but the two-dimensional representation of a three-dimensional tetrahedral organelle molecule by projection. So if you look at a molecule like this is a three-dimensional representation of a molecule, and this three-dimensional representation he want to put in a two-dimensional way. So that is how he was thinking, and he made this Fischer projection. So in this Fischer projection, he mainly used it for depicting the structures of carbohydrates, and later on it was also used to represent amino acids. So how he actually did this? Basically, when we use the word projection means something is put on something. So if you say a shadow, projection is nothing but a shadow. So if this molecule is in the three dimension, so if this molecule is in three dimension, if this is projected on a two dimension, that means we are basically going to see the shadow of this molecule, and from that shadow he started writing the structures. So how it happens is basically we are going to put a light from the top. So these molecules, each atom or a group will be projected on a plane, basically on any surface. So let us say this is the wall. On the wall it is being projected. So the tetrahedral arrangement is actually represented in the form of straight lines, basically on a two-dimensional one, like a square planar one we could represent. So this is how, this is for the four atoms only which is surrounding the central carbon atom. If we have to write other things, we will see how the Fischer projection can be written for other molecules as well. So here each letter is projected on this wall like this. From this we can actually find out what is the actual stereochemistry of the starting material or the material on which we have done the projection. So before we move into the next one, we do need to know there is something called the capital D and capital L, which was first proposed by the Fischer. So this is the Fischer notation. And simultaneously, people were also talking about the small d and small l, which is dextro and levorotatory. So in other words, the DL basically corresponds to the configuration of the molecule. In other words, the spatial arrangements of atoms or groups around the stereogenic center is the DL representation or DL notation. In this particular DL system, we are talking about the relative configuration of the molecule. That relative configuration is with respect to a standard molecule called glyceraldehyde. That means the enantiomers of glyceraldehyde is used as the standard, and with respect to this glyceraldehyde, the other compounds are given D and L based on how the groups are actually placed. And when we say it is small d and small l, what we are referring to is basically dextrorotatory and levorotatory respectively. So this is used to designate the sign of optical activity. That means if a tetrahedral carbon has 4 different groups or atoms, then we say it is a chiral compound. And whenever we have a chiral compound, the chiral compound rotates plane polarized light that we have seen earlier. So whether it rotates the plane polarized in the right hand direction, then we call that as a dextrorotatory substance. If it rotates in the left hand direction, we call it as a levorotatory substance. So the small d and small l represents basically the optical rotation of the molecule. Now, you have to remember this very importantly. The configuration and optical activity are basically two independent features of a molecule. They are no way related to each other. The configuration can be assigned to a stereogenic center. That means if a molecule has more than one stereogenic center or a chiral center, then what we can do is we can assign the configuration D or L. Similarly, R and S notation is also used, which we have seen earlier, for the configuration. So the D and L or R and S are basically configurations which can be assigned. And when we talk about optical activity is basically for the whole molecule. Of course, when we use capital D and capital L, that is mainly used for carbohydrates and few amino acids only. For a complicated molecules, we cannot assign D and L because each stereogenic center cannot be assigned. This we will see later. So how to do the Fischer projection? It is given here. So as we mentioned, the main carbon chain is drawn in the vertical line. So this A, the center carbon C and Y, all this vertical line basically contains carbon atoms or carbon chain is written in this vertical line, and all this vertical line represents bond behind the plane or below the plane. So if you look at here, we will soon see the three-dimensional representation of this one. And here this atom and this atoms are actually pointing away from the observer, and these two are pointing towards the observer. So that means the bonds or the substituents that are drawn in horizontal lines are basically representing the groups or atoms which are in the front or they are above the plane. So this is how the difference, the top and the bottom are behind, the left and the right are in front. So this is how the Fischer projections are written. Now we will see the three-dimensional representation for this molecule to see how it is actually done. So this is the three-dimensional representation which we were discussing right now. So these compounds which are in the vertical line are basically pointing away from the observer. If I rotate the molecule, you can see that very carefully. So these two, the things which are on the vertical axis are behind the plane or away from the observer. And if you look at the groups or atoms in the horizontal line, they are pointing towards the observer. So if you look at these two are pointing towards the observer. So that way we can represent the three-dimensional structure in a two-dimensional plane according to Fischer projection. So remember once again, the groups or atoms, especially the carbon atoms which are in the vertical line are behind the plane. So this is behind, it is not in the front, so it is behind. And anything that is drawn in the horizontal line or towards the observer, it is pointing towards the observer. So this is the one you have to remember. So this is how generally the Fischer projection is written for the entire molecule. So we have mentioned in the DL Fischer projection, the standard which is used is the D-glyceraldehyde. So in the case of D-glyceraldehyde, what we do is the highest priority group, the hydroxyl, is on the right hand side. So how to draw the Fischer projection? We will see this first, then we will go back to the previous slide. So when we draw the Fischer projection, the carbon atom 1, which is the most oxidized carbon, is written at the top. In this molecule, if you look at, we have an aldehyde group, we have a primary alcohol group. So between the primary alcohol and the aldehyde is the most oxidized one. So this is written at the top. So this is the step number 1. And then all the other groups are written in this molecule. And when we have to identify the D and L projection, what we have to look at is the last but one carbon or farthest from the top one. So in this particular case, we have only 1, 2, 3. 3 carbons are there. So we have to look at the second carbon. And in this second carbon, the hydroxyl group is on the right hand side. So when the highest priority group hydroxyl is on the right hand side, this molecule is called as D-isomer. That means this is a D-glyceraldehyde. Let us go back to the previous one. So in this case, we have written the same molecule in the three-dimensional way. So in this one, the hydroxyl group, this is the CH2OH, which is at the bottom, so which is shown here. And this is the second carbon where the hydroxyl is on the right hand side and the hydrogen is on the left hand side, and in the aldehyde group is at the top. So this is how glyceraldehyde is written in three-dimensional way. So for this one, the second carbon, that is the last but one carbon, has the hydroxyl on the right hand side. So this is the D-isomer. And when we come to the other enantiomer of the D-glyceraldehyde, which is the L-glyceraldehyde, the hydroxyl group is on the left hand side. So at the bottom carbon, it is the same. The CH2OH is the bottom one and the aldehyde is the top one. And in the second carbon only, the hydroxyl had changed their position because it is the enantiomer of this one. So in this particular case, the hydroxyl group is on the left hand side. So this is called L-glyceraldehyde. So for convenience, you can remember L is for left. So that means if the highest priority hydroxyl is on the left, then you say that is L-glyceraldehyde. So that way you can easily remember between whether the highest priority group is on the right hand side or left hand side. Simply remember L for L. That means left for L-isomer. So that way you can easily remember this. Now we will see the three-dimensional representation of these two molecules. So this is the glyceraldehyde. Here the hydroxyl is on the right hand side. So this is the D-isomer. Let me rotate the molecule so that you can see how it is actually projected. So as we mentioned, the carbon chain is actually pointing away from the observer. So we have to write like this. So the central vertical axis has all the carbon atoms and they are basically projecting away from the observer, which is very clear from this one. So these two carbons are away from the observer. And then we write the other groups in the horizontal way. So here we have only one hydrogen and one hydroxyl group. So the second carbon has hydrogen and hydroxyl, and this is present in the right hand side. So this representation is nothing but the D-glyceraldehyde. So this is the standard which is used in Fischer notation. Now let us look at the other enantiomer, that is the L isomer, that is the L-glyceraldehyde. So here again, the vertical axis, if you look at carbon 1, 2, 3, all the three carbons are in the vertical axis. They are pointing away from the observer, and then the hydrogen and the hydroxyl, which is written in the horizontal way, are pointing towards the observer. So if I am the observer in the front, so these two atoms are pointing towards me. And in this particular case, the hydroxyl group is on the left hand side. So as we remembered, L for left. So if the hydroxyl group is on the left hand side, we have the L isomer. So this is nothing but the L-glyceraldehyde. So this way we can actually see the three-dimensional representation as well as the 2D Fischer notation for this molecule. Let us look at some of the characteristics of Fischer projection. Because this is very easy to visually see the stereochemical properties of a carbohydrate, that is mainly the monosaccharide. So this method is famously used by Fischer and being followed by other people also. And basically this Fischer projection uses monosaccharides basically in the case of carbohydrates in its open chain form. So we are not talking about the cyclic monosaccharides, we are only talking about the open chain form. And moreover, each monosaccharide has different names like ribose, arabinose, xylose, glucose, based on whether they are triose, tetrose, pentose or hexoses. It is very easy if we tell whether it is a D isomer or an L isomer, we can easily identify which isomer we are referring to, because this, especially the monosaccharides, the triose, tetrose, pentose and hexoses, all of them have a very specific name, and mentioning D or L exactly tells which enantiomer we are discussing about. So that is the reason Fischer projection was very famous and it is being used for many years, but later on it was not used except in the case of carbohydrate. Fischer notations are not used for general organic chemistry compounds. We have R and S nomenclature. We will also see why the Fischer projection cannot be used for other molecules soon. And do you know one important factor? The naturally occurring carbohydrates are basically D isomers, whereas the amino acids are L isomers. So the natural selection is a very characteristic one, and no one knows what is the reason why carbohydrates are having D and amino acids are L. No one had found out what is the reason for this so far. Although many proposed theories are there, but none of them is finally accepted. Here, as I mentioned, we are looking at a few of the examples of D and L isomers. Here we have written the D-glucose isomer, and the D-fructose isomer is also written here. In both the cases, if you remember, how do we assign the D and L? The most oxidized carbon is kept at the top. So in this particular case, we have an aldehyde group that is kept at the top, and the CH2OH is at the bottom. and the carbon which is farthest from the top, that is, this is the carbon which is far away from the top carbon. So in this particular carbon, whether the hydroxyl is on the right hand side or the left hand side decides whether it is a D isomer or L isomer. So in this particular case, the hydroxyl group is on the right hand side, so this belongs to D isomer, and the representation of the hydroxyl group in this particular molecule is glucose. So this isomer is the D isomer. Like that we can easily deduce the structure. And when we look at the D-fructose, there is one challenge, because if you look at the top carbon, this is the CH2OH, which is a primary alcohol. The bottom one is also a primary alcohol. So in this particular case, whether this group will come at the top or this one will come at the top is the competition. But in that case, what we have to do, we have to look at the second carbon. So in this second carbon, we have a ketone. In this one, we have a hydroxyl. So there is a difference between the secondary hydroxyl and the ketone. Ketone is the most oxidized functionality. So the compound is written like this by keeping ketone at the top, and now the farthest carbon is this carbon, and this is having the hydroxyl on the right, so this is again a D isomer. And the same way, if we talk about D-valine, in this particular case we are actually going to look at this chiral center, and as I mentioned, all the normal, naturally occurring amino acids are L isomer. So L means this amino group is on the left hand side, and in this particular case, we have actually, this is the mirror image written in a different way. So that is the reason you will see these groups are basically interchanged. So I will show how it can be done. By keeping one of the carbon and this bond fixed, we can actually rotate all the three groups in a clockwise or an anti-clockwise direction in the Fischer projection. That always gives the same configuration. So if we have to do the same way, what will happen is, now the carbon chain is in the main projection. So that means this is the carbon number 1, this is another carbon, this is another carbon. So we have 3 carbons. So the most oxidized one is written at the top, COOH, and the second carbon, and we have the third carbon which is at the bottom one. So in this particular case, the NH2 group is on the left hand side, so this is the L isomer, and the hydrogen is on the right hand side. But in this particular case, we have to actually rotate the molecule little bit, because this group is actually pointing towards the observer. So this is not the right representation of the Fischer projection, because as according to Fischer projection, all the groups, all the central carbon chain has to be away from the observer. So since it is pointing towards the observer, what we do need to do is, we have to rotate the molecule in such a way that this goes behind. So in this particular case, we have to rotate all the 3 groups. So this has to go here, and this hydrogen has to come here, and this NH2 has to come here. So that way we can rotate all the 3 groups in a clockwise direction. So that leads to, now the NH2 group is on the right hand side. So the actual representation can be like this. So here it will be the hydrogen molecule, and this is our acid part, and here we have the NH2, because these two are now pointing towards the observer. And then what happens is the CH3 group, which is at so this group is now pointing away from the observer. So that means this acid group and this methyl isopropyl group and this central carbon, all the 3 are in the straight chain, that is perfectly fine in the vertical line, and these 2 are now pointing away from the observer. That is the reason this NH2 is on the right hand side. So even though whichever way we draw the molecule, before we assign whether it is D or L, we need to rotate the molecule in such a way that the central carbon chain compounds are actually pointing away from the observer. So this is one of the things you have to do. So even though we draw in any fashion, before assigning D and L, we do need to do the proper rotation. So that is the reason this example I had shown here, so that you can easily understand the difference. And when we look at the other L isomer, we already know this carbon is the most oxidized one. So this is kept at the top and the CH2OH is at the bottom and the hydroxy group is on the left hand side. So this is the L isomer. So that way we can easily identify L for left. And when we talk about ribulose, what happens is the second carbon is the most oxidized one and this hydroxyl is on the left hand side. So again this is the L isomer. So this way you can easily find out what is the D and L isomers of that particular compound. Now we can compare Fischer projections with R and S notation, because this R and S notation is the most accepted one in organic chemistry, whereas Fischer projections are even now the most prevalent one in the field of carbohydrate chemistry. So we are taking a simple amino acid, that is here we are taking a lactic acid. So we have a hydroxyl group and we have a methyl group, carboxylic acid and hydrogen. So according to the R-S nomenclature, we already know the hydrogen should be away from the observer. So in other words, we have to rotate the molecule in such a way that the hydrogen goes behind and the methyl group will come here and the OH will come here. So that way we can actually rotate the molecule, and when we rotate the molecule, the highest priority group, that is hydroxyl, will be here, number 1, and the next highest priority carboxylic acid is second one because it has oxygen and carbon. Methyl will get the third priority, which will be here. So 1, 2, 3. So this is in the counterclockwise direction. So this is the S isomer. So that way we know how to give the R-S notation for this particular lactic acid, and this lactic acid can be written in this way. So how do we write here? We know the methyl group, this carbon and this carboxylic acid. These are all the 3 carbon chain in this particular molecule. So we have to write them in the vertical line. So when we write these 3 groups, that is carboxylic acid at the top, the carbon, the second carbon is here, and then the methyl group. So all these things are written in the vertical line. Now the OH is on the left hand side, so we write the OH on the left. The hydrogen is on the right hand side, so we write the hydrogen on the right. So this can also be written like this. So this is another way of representing the Fischer projection for lactic acid. And if you look at the other isomer, that is the enantiomer, so in this particular case H and OH are interchanged. So obviously what the compound we are going to end up is a R isomer, and this R isomer can be represented like this. We know if the hydroxyl is on the right hand side, then we can say this is the D isomer, and the hydroxyl is on the left hand side, so we say this is the L isomer. So that way we can also give either R and S notation for the compound or D and L notation for the compound by simply writing the molecule in this fashion. So irrespective of whatever the groups are there, you can actually interchange the groups to get the right orientation. Now some of the rules are which are employed for the interconversion of Fischer projections. The first one is, if you rotate the Fischer projection by 180 degree, that retains its configuration. So what does it mean? So what we are rotating is the CHO group is now coming at the bottom and the CH2OH group is going to the top. So in that case what will happen? The OH will also come here and the hydrogen will come and shift here. So we are actually rotating the whole molecule. So that is why the hydrogen is shifted to the right and the OH is coming to the left and the most oxidized group, that is the aldehyde group, is at the bottom. The CH2OH is written at the top. So if we write this way, again what we are meaning, we are writing the same molecule. We are not doing any change. That means the configuration of the molecule is not at all disturbed or not at all changed. So we are getting one and the same stereoisomer in this particular case. Now, if we do the rotation by either plus or minus 90 degree or plus or minus 270 degree, both these changes, interconversions, leads to inversion of the stereochemistry at the center of rotation. So this is the center. Here we have only one carbon, so we are just talking about this particular center. So here we are doing a 90-degree rotation. So what do you mean by 90-degree rotation? We are simply moving the CH2O to here. So what happens? Every group will move one place. In the previous case, every group moved two places. So here it will move only one place. So the OH will come here and the CH2OH will come here and the hydrogen will go up. So hydrogen at the top, CH2 at the right, OH at the bottom, CH2OH at the left hand side. So here basically, so here the H is missing, so I just wrote that H here. So it is basically CH2OH group here. So in this particular case, the 90-degree rotation basically gives the different stereoisomer. So why we say this is a different stereoisomer? If we take the simple configuration of this molecule, then that will actually give a different isomer. So that is the reason we say 90-degree rotation or 270-degree rotation leads to inversion of the stereochemistry at the center. Because how do you give that now? What you have to do is basically every group, the oxidized group, has to be changed. Now in this particular case you will see the rotation, how it actually affects. Here what we are doing, that is we are rotating 90 degree or interchanging two substituent. So the methyl group at the bottom and the carboxylic acid at the top remains the same. There is no change. But we are now interchanging only two groups. So this is interchangeable to here and this is interchangeable to here. The other two groups are not at all disturbed in this particular case. So in that case what will happen is the S isomer becomes R isomer, or otherwise if you say this is the, in this particular case, the carboxylic acid most oxidized carbon is at the top, methyl group is at the bottom, and the hydroxyl is on the left hand side. So this is the L isomer, and in this particular case this is the D isomer. So that means L becomes D. That means we are actually interchanging the configuration at this particular center. So this is what is the rotation by 90 degree leads to this particular change. Now another type of interconversion, in this particular case what we do is we keep one of the group constant. We are not moving this group. We can rotate all the other three groups in a clockwise direction or an anti-clockwise direction. So in this particular case what we are doing, the CHO is written at the top and then the hydrogen is moved to the right. So here then the OH comes down as shown here and this CH2OH come to the top. So like here on the left. So this way when we rotate, we are actually having the same stereoisomer. We are not doing any change. So these are some of the ways by which the Fischer projections can be interconverted. Let us deal with some of the issues of Fischer projection. See, these are all the reasons why Fischer projection is not at all being used in general organic chemistry. It is mainly used only in carbohydrate chemistry, because this is not an accurate representation of the 3D structure of the molecule. Mainly when there are more than 3 stereogenic centers are there, this method DL configuration cannot be applied to the whole molecule. Because another major problem which we will see now, that all horizontal lines are considered to be projected towards the observer. and this is not the case actually. So that means when we write the zigzag representation of the carbon skeleton, and if the C1 has the two atoms or groups projecting towards the observer, then the carbon 2, it is not necessarily the top carbon or the bottom carbon. Any two adjacent carbon is the one which we are representing here as C1 and C2. Okay. The second carbon will have two groups projecting away from the observer. That means they, in the zigzag representation, basically what happens is two groups are pointing towards the observer, and the immediate carbon, the next two groups are actually pointing away from the observer. And if you go to the another adjacent carbon, in that particular case it will again come back to the towards the observer. Like that it will go. We will see the three-dimensional representation and we will understand what does it mean by this. So in other words, we cannot basically write C1 and C2 by vertical lines. So this is the problem. Let us look at the three-dimensional representation to understand this problem. So let us look at the limitation of the DL notation or the Fischer notation. So what we saw earlier was all the see, the main vertical line is the carbon straight chain. Okay, so this is the carbon straight chain, so we don't have to worry about this right now. But what we have to really worry about is the horizontal lines. So according to Fischer projection, all the horizontal lines are pointing towards the observer. But unfortunately, in reality, if we draw all the carbons in the straight chain mode, so that means this is basically the zigzag representation which we were talking about. And if you look at this zigzag representation, what happens is the carbon chain, okay, we can consider this is in the straight chain, so vertically we are drawing that. But let us say I give this as the first carbon. So in this first carbon, these two groups or the atoms are pointing towards the observer. Whereas if you look at the second carbon, in this carbon, these two groups or atoms are pointing away from the observer. I just rotate it, then you will see the difference. So in the first carbon, two are pointing towards the observer. In the second carbon, two are pointing away from the observer. In the third one, it is pointing towards the observer. So this way, when we are representing all the carbon atoms, every alternate carbons will be wrongly represented by the DL projection. So in order to write this in the same way, when a person is pointing towards the observer, then what will happen is this group has to come here and this group has to come here. So every other carbon, we have to twist the molecule in order to write the proper Fischer projection for that particular molecule. So this is the major limitation, and not many people are very comfortable in representing this. So it was abandoned for the normal organic chemistry molecules. Basically the entire except the carbohydrate chemistry, none of the other field was very happy to use these kind of complicated structures. Let us now study about the reactions of chiral molecules. So we will be now studying about the reactions involving stereoisomers. We have various types are known. We will first study about conversion of a achiral molecule into a chiral molecule. That means we are going to generate a new chiral center. Next we will be studying about Next, we will be studying about reactions of chiral molecules involving centers other than the chiral center. Then we will also study about reactions with where the second chiral center is created without disturbing the existing one. Then we have reactions of chiral compounds with optically active reagents. Then finally we have reactions of chiral compounds at the chiral center. So we have various reactions. We will see one by one right now. The first one is conversion of an achiral molecule to a chiral molecule. That means generation of a new chiral center. So we have a achiral N-butane molecule as shown here. This is treated with the chlorine in the presence of either heat or photo reaction, leads to a secondary butyl chloride and N-butyl chloride. So that means basically the chlorination occurs on any one of the carbons, that is either at the terminal carbon or the internal carbon. So in this molecule, whether it happens at this end or this end, it is one and the same. So we have only two types of chlorination. One is at the terminal carbon, the second one is in the internal carbon. So when the chlorination happens in the terminal carbon, we have CH2. So two groups are same on this particular carbon. So there is no chiral center at this particular carbon. When the chlorination takes place at the terminal one, we are not getting any chiral compound. But on the other hand, if the chlorination happens in the internal carbon, that is the last but one carbon, we have four different groups attached to this particular carbon now. One is a methyl group, another one is a chlorine, another one is a ethyl group, and the fourth one is a hydrogen atom. So we have four different groups on this particular carbon. So this internal carbon now becomes a chiral center. Now when we say chiral center, we can actually have in this particular case two types of products, that is two stereoisomers are possible. One is the S isomer, another one is the R isomer. So this is a secondary butyl chloride. So we say it is S secondary butyl chloride or R secondary butyl chloride. This plus and minus sign represents the optical rotation. The capital S and capital R represents the configuration. So these two are two different things. So in this particular case, the chlorine is on the right hand side, methyl group is written at the top, ethyl group is written at the bottom, and hydrogen is on the left hand side. So this is how basically this is nothing but the Fischer projection we have written here. And if we have to look at R and S nomenclature also, we can actually do. The hydrogen has to go behind the observer. Then we have to give the highest priority groups. So the chlorine gets the highest priority number 1, followed by the ethyl group, followed by the methyl group. So this is 1, this is 2, this is 3. Since the hydrogen is pointing towards the observer, if they are in the clockwise direction, then what we end up is basically the opposite isomer, that is the S isomer. And the same way here, if you look at, the chlorine is having the highest priority, ethyl group is at the bottom, methyl group is at the top. So this is in the counterclockwise direction, but the hydrogen is pointing towards the observer. So whenever we have the hydrogen, that is the least priority group, pointing towards the observer, whatever is the clockwise or the anti-clockwise rotation will lead to the opposite configuration. So that means if it is in the 1, 2, 3, so this is in the counterclockwise direction. So that means hydrogen is actually pointing towards the observer. So that leads to negative of negative. We have to think in that way. So the observer, the hydrogen has to be away from the observer. So that is where the actual configuration is assigned. But in this case, we have hydrogen pointing towards the observer. So whatever we get, we have to just reverse it. So in this particular case, this is the counterclockwise one, that is the S1, so that we have to reverse. So the actual configuration is R isomer. So that way we get two enantiomers in this particular reaction. Now, how the reaction actually proceeds? So in this particular case, the chlorine atom basically forms there is a flat free radical intermediate that is formed in this particular reaction. So the central carbon is having the free radical. Now the chlorine molecule can attack this radical from either side A or from side B. So in this particular case, we have equal probability of this chlorine atom attacking this radical, because this is a planar radical. So there is no difference in whether it will attack from one side or the other side. So we end up with both the products. That means both isomers are formed in equal proportions. So in other words, whatever we say is, if the starting material is a achiral one. If we are not using any chiral substances or the reagents in that particular reaction, the obtained products are actually going to be achiral only, because we are going to get 1:1 mixture of both the products. In other words, we are going to get racemic modification. So now, as I mentioned, this synthesis of chiral compounds with an achiral reactants always is a racemic modification. We need to answer why this always happens. As I mentioned, we are going to get both the products, but both the products are going to be formed in 1:1 ratio. In other words, if one isomer rotates the plane polarized right in the right hand direction, the other isomer will rotate the same light in the left hand direction. So that means 50-50 mixture of right and left will cancel each other, and the net optical rotation is 0. In other words, the compound is going to be optically inactive. So we can also talk the same in terms of energy of activation, because in this particular case the energy of activation for the isomer R is exactly same as the energy of activation for S. In other words, the rate of formation of R isomer is exactly equal to the rate of formation of S isomer. In that particular case, both are formed in 1:1 mixture. So that is the reason we are actually going to get optically inactive or racemic modification in this particular case. So we can conclude that whenever we have a achiral starting material and the reagents and the reactants that are used in this particular reaction, which is achiral, will always give racemic modification only. We cannot get any chiral substance, chiral compound from this particular reaction. So next we will be looking at another reaction. Here the reaction of a chiral molecule involving centers other than the chiral center. So we will take the same example, the secondary butyl chloride. We already know this is a chiral center, and this now can undergo chlorination. So this undergoes chlorination to give another product, that is the 1,2-dichlorobutane is formed along with many other products. So we are starting with the starting material, that means the secondary butyl chloride. So as we mentioned here, the 1, 2, 3, this is in the clockwise direction. Hydrogen is pointing towards the observer. So 2 negative we have to do. So that means this isomer is nothing but the S isomer. And this undergoes chlorination. So the methyl group, the proton is subtracted and we get a CH2 radical here. This again undergoes reaction with the chlorine molecule to give CH2Cl. So in this particular case, what happens actually? The chlorine is again the highest priority group. Now, instead of the ethyl group, here in the methyl group, the first carbon is same. Both are carbon only. And if you look at the other attachment to this carbon, we have 2 hydrogens. Here also in this particular case, we will be having 2 hydrogens. The third one is a methyl group, but in this particular case we have a chlorine. So the third substituent on this particular carbon has a highest priority compared to this one. So the numbering changes now. So this becomes the highest priority number 1, this followed by number 2, and this ethyl group now becomes the third priority group. Since the hydrogen is pointing towards the observer, now we have to do negative of negative, so that means opposite of opposite. So 1, 2, 3. So this is in the counterclockwise direction or in the S, similar to S isomer. Since hydrogen is towards, we have to convert that S into R, so we become a R isomer. Now the question will arise. The reaction did not change the configuration of this particular carbon because no bond is broken in this particular carbon, because the chlorine remains here on the right hand side. In the product also chlorine remains there on the right hand side. Hydrogen remains on the left hand side. Hydrogen remains on the left hand side. The ethyl group also remains at the bottom. Ethyl group remains at the bottom. The methyl group also did not change. Here also instead of methyl, one group, one atom is replaced with another atom. That is the only thing. So that means this carbon-carbon bond is not broken, carbon-halogen bond is not broken, carbon-hydrogen bond is not broken, and this carbon-carbon bond is not broken. So in other words, we did not even break any single bond at the chiral center, but the configuration for the starting material is S, but for the product is R. So how does this change happen? So this is the one thing you have to always remember. Depending on the substitution of atoms or group in any one of the carbons surrounding the chiral center, if the priority changes, basically the compounds R and S nomenclature changes. But that does not mean that we cannot simply or blindly say S isomer cannot give R isomer without bond breaking. So you have to always remember an S isomer without breaking a bond can also give an R isomer. That is the reason you have to always draw the structure of the starting material, which is the S isomer, and the product, which is the R isomer. Then you compare whether there is any bond that is broken in the reaction at the chiral center or the center. So this is what you have to always remember. You cannot blindly follow that whenever there is a reaction in which the chiral center is not broken, need not change the R and S notation. There is a possibility, as shown here, the R and S can change even though the chiral center did not break any bond. So you have to look at the entire molecule for the change and not at only the single reacting center. So what we say in this particular case, even though S and R changed, we should not say this there is a change in configuration. We have to say in this particular case it is a retention of configuration because there is no bond that is broken at the carbon center which underwent, which is the chiral center in this particular case. Because the reaction happened at the center other than the chiral center. So that means when a reaction occurs any place other than the chiral center, we don't care because the absolute configuration or the configuration of that particular chiral center will not change. So the next one is the configurational relationship of basically two optically active compounds can be determined by converting one to other that do not involve breaking of a bond at the chiral center. So this is the extension of the previous one. So we already know when there is no bond in the chiral center is broken, that means the configuration of the starting material and the end product are going to be the same one. Irrespective of whether both are R isomers or S isomers, it doesn't matter. We can draw the structure and conclude that this is actually the reaction where there is no carbon or other bonds at the chiral center is broken in that particular reaction. So in this particular case, we have an alcohol, primary alcohol. This is treated with the hydrogen chloride to give the halo derivative. Alkyl halide is formed. So this carbon is the central chiral carbon, and this carbon there is no bond broken because carbon to this methyl group or this ethyl group or this hydrogen or this CH2, none of these four bonds are broken in this reaction. In other words, we can say the starting material and the product will retain the same configuration. Okay. Of course, in this particular case, the starting material, the hydroxyl is having the highest priority. Chlorine is also having the highest priority. So if it is a S isomer, we will still have the same S isomer. It will not change. But now you observe here, this starting material is having a negative optical rotation, whereas the product is having a positive optical rotation. So as I mentioned earlier, the configuration and the optical rotation are independent of each other. We don't have to say all the time S isomer will be the minus rotation, having minus rotation, and R isomer means it is always having positive rotation. We cannot say that. So configuration as well as optical rotation are two different things. Now there is another reaction we can look here. If we start with the primary alcohol, that is CH2OH, this can undergo KMnO4 oxidation to give a carboxylic acid. So in this particular case also, the chiral center, there is no bond that is broken in this particular starting material. So this carbon-carbon bond, this carbon-methyl bond, carbon-ethyl bond or carbon-hydrogen bond remains intact in the product also. What happens is only the carbon which is away from the chiral center, that some change took place. So in this particular case also, the S isomer remains the S isomer. There is no change because the priority group OH is already attached to this carbon. Here again we have the carboxylic acid attached to this carbon. So that means this is the highest priority group in the product. This is the highest priority group in the starting material. So they remains or retain the same configuration, that is S and S. Here again, if you look at the optical rotation, the starting material is the minus isomer, product is a plus isomer. So it can happen in any reaction. So the next one is reactions involving, that is chiral compounds are reacted with optically active reagents. So this is basically nothing but resolution. In other words, a racemic modification is converted by an optically active reagent to a mixture of diastereomers which can then be separated. So we will be studying about this in the next few sessions elaborately. Then the last one is relating configurations, because when there is no bond that is broken at the chiral center, configurations are retained. This we already know. So we have both the examples shown here. Here the hydroxyl is converted to chloride, no bond breaking, so the configuration is retained. Then in the other case, the secondary butyl S is converted to R. Here again, there is no bond is broken between the carbon, that is the chiral center. So here again there is another example which we are actually recapping what we have seen so far. So the hydroxyl is converted to either chloride or carboxylic acid. In all the cases, the S isomer retains the same configuration, S and S. The last one is the generation of second chiral center. In this case, there is no bond is broken at the chiral center and the configurations are retained. But if there are two possible configurations at the C3 here when it undergoes the reactions other than the chiral center. So in this particular case, the reaction occurs other than the chiral center. So this is the chiral center, there is no reaction here, but this is the carbon where the reaction occurs, that is generation of a new chiral center happens in this particular case. So if we follow the same explanation like what we did earlier, in this particular radical reaction also the chlorine can attack this carbon radical from either side A or side B with equal probability. In other words, we will have two diastereomers formed in this reaction. But one difference may happen is if the chlorine is on one side, maybe this chlorine attack from this side may be hindered because of chlorine's electronic clouds repulsion is possible. In that case, the chlorine may sometimes a little bit preferably attack from the side B. So these kind of very small minor differences are possible, but this is not a major case. So the product yield may be like instead of 50-50 ratio, we may get something like 48-52 or 47, 53 in that ratio we may get. So we may end up with a pair of diastereomers in this particular reaction. In summary, let us recap what we have studied so far. We have studied about Fischer projection, how the idea of projection started to Fischer, and then what is D and L notations, that is capital D and capital L. The standard compound used was D-glyceraldehyde and L-glyceraldehyde, and how to assign DL notation to various carbohydrates. We also studied about interconversion of Fischer projections, like a 90-degree rotation leads to whether the 90-degree rotation leads to the same isomer or a different isomer, and what about the 180-degree rotation, does it give the same isomer or a different isomer. So all these things we have studied. And we also studied about reactions involving stereoisomers, that is generation of a chiral center from a chiral molecule, reactions involving centers other than the chiral center, that is the bond breaking takes place at a place other than the chiral center, and we also studied about reactions of chiral compounds at the chiral center. With this we conclude this session. Thank you.